So the problem, the scientific problem in the spirit of Richard Feynman, is to do the following. We want to guess about how this structure emerged, and then we want to do experiments. But we want to do experiments back here. What we really want to do is build a time machine and sweep back to the first billionth of a second after the Big Bang or before and observe what's happening in the universe. We can't do that, unfortunately. But what we can do is recreate those conditions in a lab. The conditions of very hot, very dense, very energetic space. And this is the lab that we do that at. It's called the Large Hadron Collider at CERN in Geneva. 27 kilometers in circumference. It's the biggest scientific experiment ever attempted, the biggest scientific experiment ever built. This is in 2 countries. Most of this, at the bottom of the picture, is France. The top of it is Switzerland. That's Geneva Airport runway. If you've ever been to Geneva, you would have landed on that runway there. So that's an airport. The experiment we built dwarfs an airport. Its job is to take the nuclei of hydrogen, so the simplest element, single protons that make up the atomic nucleus of hydrogen, and accelerate them to 99.999999% the speed of light. Right, an immense number. That means, in more visualizable terms, that they go around this 27-kilometer ring 11,000 times a second. And we do that with 2 beams of protons. One we send around one way, one we send around the other way, and we collide them together. In those collisions, and by the way, we can collide up to 600 million protons together every second in the Large Hadron Collider. In every one of those collisions, we reproduce the conditions that were present less than a billionth of a second after the universe began. So, what are we looking for? Why did we build this immense machine? Well, as of today, as of now, then this is what we know of the universe. So we know today that the universe is built of just these things. These are the fundamental building blocks of the universe as of now, as the Large Hadron Collider begins to take data. Some of them may be familiar. This one may be familiar. This is the electron. So the first subatomic particle to be discovered, the first fundamental one to be discovered, the thing that goes around the atomic nucleus to make atoms. These 2 things may be slightly familiar. They're called up and down quarks. The proton is made of 2 up quarks and a down quark, and the neutron is made of 2 downs and an up. So those 2 things are the building blocks of the atomic nucleus. And that's what you need to build you and me and the Earth and the stars and planets and everything we can see in the sky, every galaxy that we can see, we think is made of just those, the up and the down quarks and the electron. This thing, called a neutrino, completes the set of these 4. It's a kind of unusual particle in a sense. You may not have heard of neutrinos. Actually, they're intimately involved in the way that the sun shines. And in fact, in the process, the sun goes through converting hydrogen into helium. It produces copious quantities of these things called neutrinos. So many, actually, that if you hold your thumbnail up now, which is about a centimetre square centimetre, there is something like 60 billion neutrinos per second going through your thumbnail from the sun, and through every square centimetre of this room. You don't feel them because they interact very weakly with normal matter, but they're there and they allow the stars to shine. So they're important, and that's all you need to make a universe as far as we can tell, just those 4 particles. For some reason that we don't understand at all, nature saw fit to make 2 carbon copies of those, as it were. Now, carbon copies you probably don't know anymore because you don't do that, you scan things in. But 2 precise copies of those 4 particles. These are identical in every way to those 4 particles, except they're heavier. So this thing is called a muon. It's the same as an electron in every way except it's heavier. This is the tau. Same as the electron and the muon in every way except they're heavier. We have no idea why nature chose to do that. They don't seem to be any use, but we've discovered them. So we have reasonably good evidence that there aren't any more. So that's one of the great mysteries in physics, actually. Why has nature chosen that pattern? You only seem to need 4 to build everything. Nature has got 12. We don't know why. That's one of the mysteries. But the other mystery, we don't know anything about that, by the way, so we don't really know how to look. We just hope that something will crop up, someone clever will come up with some kind of theory. But there is something much more specific that we're looking for, which I can demonstrate with an equation. Now, I apologize about putting an equation up. Some of you might not like equations. This one, though, is worth looking at because it's incredibly simple in many respects. This equation I'm going to put up now describes everything we know about the universe except gravity. So everything from the way atomic nuclei work, the way that atoms and molecules stick together, the way that light interacts with atoms and molecules, the radioactive decay, the way stars shine. At a fundamental level, everything we know about the universe at the start of the 21st century is in this equation. It might not look simple to you. It doesn't look simple to me very often. But if you think about it, it's rather amazing that you can write down a piece of mathematics that describes every phenomena we know of in the universe other than gravity in such a simple and beautiful way. But there is a problem with it. I'm tempted to say, can anyone see what it is? But that would be unfair, wouldn't it? The problem, actually, it's not a problem really, it's a prediction, lies in these last two lines. See, the first two lines contain symbols which represent all the particles here. So all those things are combined in these symbols, the forces of nature, electromagnetism, all those forces, the nuclear forces that stick the nucleus together, all described in the first two lines. The bottom two lines contain this symbol here, which is a Greek letter phi. And that represents a particle that is not here, right? So in other words, there's a particle in here that's predicted by our best theory of three of the four forces of nature that has not yet been discovered. It may not even exist, but it's predicted to exist. In the spirit of Richard Feynman, we have to go and look for it. And this is one of the key things the LHC does. What is it? Well, this thing is called a Higgs field. So this thing is called the Higgs particle that you may have heard of. It's a particle that's predicted to exist in order for our theory to work. So it's really, you sit down, do maths, it doesn't work, you find a way of fixing up the maths so it describes the things you can see. And the only way, or the simplest way we found of doing that is by introducing this new thing. What does it do? Well, it gives mass to everything in the universe. So if you look at your hand, it's made of subatomic particles and they have mass, they have substance, obviously. What we found about 50 years ago now is if you just write in the masses, you say electrons got a mass, we weighed it back in 1897 actually, let's just put it in our equations. It turns out that the whole thing fails, it doesn't work properly at all, it's unable to make predictions, it's wrong, you can't do it. So what was found by a scientist called Peter Higgs is that you can introduce mass in a very interesting way, a clever way, which actually gets around all these difficulties, makes those equations work. And it's really simple, actually. It's just simply this. The universe, says Peter Higgs, is full of a field called a Higgs field. So you might imagine that this room is full of something called a Higgs field. Inside your body, there's a Higgs field. Out to the most distant galaxy in the universe, there's a Higgs field. Everything has to pass through it. So all the particles in you are now passing through and talking to the Higgs field. The way it works is that if you think of a massless particle like light, so light's a stream of particles flying around the universe, they don't talk to the Higgs field. That means that they get no mass. They stay massless. They pass through the universe unimpeded. But the electrons and the quarks and everything that makes up your body, those things have to talk to the Higgs field. They interact with it. They get dragged back by it in some way. So they acquire mass. They can't pass through the universe at the speed of light. That mechanism, which is quite simple, it's almost like pulling something through a vat of treacle, is actually our best theory of how mass appears in the universe. If that's true, and it sounds a bit convoluted, but if it's true, then we have to find these things, the Higgs particles at the Large Hadron Collider. If it's not true, and it may not be, because it's only a theory, then we know that we will see the origin, the process, I suppose, which causes mass to enter the universe. That's kind of interesting in itself because we're saying you have substance because of this mechanism. But I think the key thing to remember is that this is our theory of three of the four forces of nature. So everything that happens in the universe other than gravity at a fundamental level is represented by this theory, and we need to know that mechanism in order to make more progress. So that's what makes the LHC exciting. And the director of CERN actually said in the press a couple of weeks ago, and I think most physicists agree with him, that if the LHC continues operating as well as it is doing now, then we should have an answer to that question within 2 years, I would say. So by the time you're finishing your A-levels and thinking about going to do physics at university, then you may be getting to university and learning about how mass enters the universe because of the discoveries at the Large Hadron Collider. So it's an exciting time to be there. It's a picture of the very early universe, which was taken by a satellite called WMAP. It's actually a picture of the universe as it was about 300,000 years after the Big Bang. That's the point at which the universe had expanded and cooled enough for it to become transparent to light. So before that time, before about 300,000 years, the universe was in some ways like a giant star. It was very hot, very dense, light couldn't travel through it. But at that point, the universe had expanded and cooled enough that atoms could form and light could travel through it. That light has been traveling around the universe for 13.4 billion years or so, and we can capture it and measure it. And this is a picture of that light. So this is a picture of the most ancient light you can ever see in the universe, captured by a satellite called WMAP. And it's actually a picture of the different temperature variations in that light. So essentially what you see, and what was known for many decades, was when you looked out into the night sky, you saw it glowing with a particular temperature, which was the echo of the Big Bang in a sense. The universe was once very hot, it's been cooling down, it's still got a temperature to this day, but it's very cold. But what was found just a few years ago was that if you look at it very closely, then you see that it's not all quite the same temperature. So there are red bits and yellow bits and green bits and blue bits. These are all different temperatures. Very, very tiny variations in temperature. Very hard to measure, but they've been measured. What we think those are the seeds of the galaxies. So we think that the beginnings of the formation of galaxies, which led to the formation of stars, planets, and us, are encoded in that light. The little dense ones, the little bits that are slightly higher temperature, were actually, anyway, a different temperature, have actually seeded the galaxies. But there's something very interesting about this, which is what I want to finish on, I think. The point is that we also have theories that tell us how those little fluctuations formed. And they're theories about how the universe behaved a millionths of a second after it began. So-called quantum fluctuations in the very early universe. So we now have theories that can take this data, we can think about events that may have happened a millionths of a second after the Big Bang, extrapolate them forward, and some of those theories fit this data very well. The most remarkable thing for me about science at the turn of the 21st century is that we've not only been able to use it for technological purposes. As Rod said, we can build iPhones, we can build satellite navigation system. We have medical science, which has transformed our lives. Our life expectancy is now not 20 or 30 years, but 80 years or 90 years. It's remarkable achievements. But actually, we've also been able to tell the story of the origin and evolution of the universe to some extent. You know, we are very, very sure that we know what happened from about a millionth of a second after the Big Bang onwards. We have a very powerful picture of that. There are things that we don't know, but we have quite a strong story about how that happened. But we also have hints that we understand what may have happened a millionths of a second after the universe began. And I think to finish, that's a tremendous achievement. I showed this picture at the start. I like it a lot. It's a picture taken by Apollo 17 in 1972 on its way to the moon. It was a picture that was taken, it's one of the few pictures that was taken with Antarctica very visible, just because of where the moon was when Apollo 17 was on its journey to the moon. The Earth was tilted. And the really beautiful thing, I think, is that it's a picture of Africa. So this is the continent of Africa dominating the image. One of the few pictures of Earth where Africa is dominant. And I think it's remarkable because if you think about it, this is the Rift Valley. So this is the cradle of humanity. This is where humans came from. Our species began its journey towards Homo sapiens. The previous versions of our species, as it were, where the oldest footprints have been found over here in Tanzania. They're only just over 3 million years old. So in only 3 million years, we've gone from the first hominid footprints, the first upright footprints our ancestors left in the sands of Tanzania, to the moon and beyond, and to be able to tell a story of the origin and evolution of the universe. How have we done that? Well, it's by the scientific method. So it's a beautiful, powerful thing. It tells powerful stories. It's not only useful, it's, I think, it's part of being human to understand about origins, evolutions, and our fate. So So with that, I will say thank you. I hope many of you want to carry on that journey, by the way. There are a vast number of unanswered questions that we have yet to answer. I'm sure some of you will play a part in answering those questions, but for now, thank you very much.